I have our graded assignments here from problem set 4, and the final one will be coming soon-ish. So don't forget, want to see your abstracts for my project. So I've discussed it with some of you, and then we can discuss some more if you have any questions. But I'd like to see a proposal, just a short abstract with particularly some of the references that you found to indicate the breadth of the project that you have in mind. Okay? Okay. So as I said, I'm happy to discuss that outside of class with any questions you might have. All right. So we're talking about light forces on atoms for cooling and trapping, fun and profit, all those good things. And we were talking about, last lecture, formulating a quantum description of such forces. And the key here is, of course, now our electromagnetic field has this corpuscular description as well in terms of photons with discrete energy and momentum. And that's going to be very important in thinking about how well we can manipulate atoms with light. And a key quantity in thinking about that is the so-called recoil energy. So the recoil energy is the energy associated with thinking about my photon as a little bullet and causing momentum recoil as the atom absorbs, or recoil as it emits as well. And that recoil energy, thus, is the kinetic energy associated with the center of mass motion of the whole atom when it has this much momentum. Okay? And we calculated, or at least we tried to estimate, how big that energy is. And if I look at it in sort of frequency units using Planck's constant, then for the alkalis, that's about 1 to 10 kilohertz. Okay? And that's important quantity to think about, that frequency scale or time scale, if I think about 1 over the frequency as a time, because the question is, there are two kinds of dynamics in principle. There's the dynamics associated with the center of mass motion of the whole atom, which is the force that we're interested in at the moment. But of course, the way in which the atom interacts with the light is through the relative motion of the electron relative to the core, the so-called internal degrees of freedom. And so that's a kind of complicated problem if you want to do all of that fully quantum mechanically. And sometimes we do, sometimes it's important. But in the initial stage, there's a kind of separation of timescales here, where because the timescale associated with the relaxation of the internal degrees of freedom when they come to steady state is set by the natural line width. And for the alkalis on a strong transition on the D1 or D2 line of the alkalis, that line width is on the order of a few megahertz as compared to a few kilohertz. It's a factor of 1,000 difference there. And so the time scale over which these internal degrees of freedom reach steady state is essentially instantaneous compared to the speed at which the atoms will move, or the time that they'll move, due to the recoil. And thus, we can think about in these initial stages as a kind of adiabatic elimination where we just think about the atom fixed at different points in space, and think about its response, and then think about its motion. Okay? So to be just a little bit more quantitative about some of this, if I wanted to have a complete, full quantum mechanical description of this process within some approximations, we can treat this interaction as a dipole interaction, the interaction with light, as we have discussed, why that's a good approximation. And we can break that up in a formal way in terms of the interaction with the mean field, the laser field, and then an interaction with vacuum fluctuations of the electromagnetic field. And if I look at this terms, the stuff that we've been studying for many weeks now, and I think about, I'm missing a piece here, excuse me. Amplitude of the field. Let's get some better job. Yep. So I've written my laser field as having some amplitude, which might be varying as a function of position. Say if it was a Gaussian laser beam, and a plane wave. Let's keep this, for the moment, we'll come back to this in a moment, but let's just for the moment just think it was a truly plane wave. Let's say there was no position dependent in the amplitude, and all the position dependence was in the phase. Then as we discussed last lecture, the quantum operator associated with this phase is a momentum displacement operator. And so the effect here of the interaction with the field has both a term related to how the internal degrees of freedom change in this two-level approximation that's either going from the ground state to the excited state, and how the external degrees of freedom change, in this case through momentum translation. And of course, if I emit, I translate the momentum in the opposite direction. So I could think about this if we wanted to have a full quantum mechanical description, including the state of that describes the internal degrees of freedom, and a part of the state that describes the external degrees of freedom, which in this case I'm thinking about it as a free particle. So my atom is not trapped. It's a free particle that's described by some plane wave, some momentum, eigenstate. Then the action of the interaction, say the positive frequency component, would be to take the atom from the ground state to the excited state and translate the momentum. Okay? So we can then just reanalyze this to understand what we were talking about last lecture in terms of what I called the recoil shift, by just thinking about conservation of energy and momentum. The question is, if I have the atom initially, say, with some well-defined momentum, P initial, in its ground state, and I want to excite it to the excited state, which will necessarily involve a recoil, a change in momentum, at what frequency should I apply this laser beam in order to resonantly drive from here to here? The answer is not just the Bohr energy difference associated with the internal degrees of freedom, because some of that energy of that photon must go into the external degree of freedom, right? And so it's a simple matter to just look at conservation of energy and momentum in this problem, and then solve for what is the frequency of this laser photon in order for this to be resonant. And here's the answer. So in the absence of motion, initial motion of the electron, and if I ignored the momentum of the photon, this is what we would say. But in addition, there are two other terms. This term is familiar. It's the familiar Doppler shift. And we know about the Doppler shift that is to say, because my atom is moving with some velocity, v, then in the frame of the atom, it does not see the laser frequency omega sub L, but it sees a shifted frequency, just due to the Doppler shift. And so the shift will be red or blue, depending upon whether or not the atom is moving with or against the wave vector, right? But in addition, there is the so-called recoil shift, which has to account for the fact that there is kinetic energy in the atom if it absorbs the photon. So the resonant frequency, even if the atom were at rest and there weren't no Doppler shift, then there would be this recoil shift. Okay? All right. All right. So, with all of that said now, we were writing down at the end of last lecture using this interaction, starting with this interaction and writing down the force operator based on this expression, but with now treating the center of mass as just a classical variable under the assumption of the separation of timescales, that the recoil energy is very much smaller than the Langmuir energy. So let me get some notes here. Right. So we define what I call the force operator due to the interaction between the atom and the laser as the gradient of that interaction. So now I'm going to allow this to be position dependent. This is what we call the Rabi frequency. So this then is equal to my two-atom raising operator, a two-level atom raising operator, plus their mission conjugate. And in the assumption now that we reach steady state, well, let me take this gradient first. So then I have a term here that's related to the gradient of the amplitude. Take all of this stuff. Term that's related to the gradient of the amplitude, and a term that was related to the gradient of the phase. And that term plus. Okay, that comes from taking the gradient of those terms. So, under the assumption, again, that we can look at the force on the atom in that it comes to steady state when the rate of spontaneous emission is very large compared to the rate at which the atom moves due to recoil. Then we can look at the expectation of this, which you remember the expectation value of this operator. If I look at this as the expectation value of that raising operator, is what we call the off-diagonal element of the density operator, rho GE. We'll look at it in steady state. All of this is in the rotating frame, so all of that goes into the phase. Plus now complex conjugate. Okay. So, again, as we've written before, this, we've called this U minus IB over 2 in my notation over here, plus, where you remember this was the real part and the imaginary part of the coherences, as we define them, related to the components of the block vector that we've discussed before. Then this has two terms, which are U over 2, the gradient of the amplitude, minus h bar k. This is the steady state solution. The steady state for 2. All right? So we see here a term that's related to the real part of this coherence, which we remembered was related to the real part of the polarizability. This was the reactive part, and this is the part that's what we call dissipative, because it's related to the imaginary part of the dipole response. And if we go back now to the solutions from the block equations, the steady state solution, we have U steady state is equal to minus the tuning over the Raman frequency times the saturation parameter over 1 plus the saturation parameter. The V steady state is minus gamma over omega S 1 plus S. And thus what we have are two expressions, the reactive force is equal to minus over delta over omega radian of omega times S over 1 plus S. And the dissipative force in this description is equal to h bar k times gamma over 2 S over 1 plus S. So let's first look at this term. It's easier to understand immediately. We remember that this, if we go back to our earlier discussion about absorption emission of photons by atoms, that this is what we call the scattering rate. Right? And that scattering rate was just equal to the incident intensity times the absorption cross-section over h bar omega. Because the absorbed power is the scattered power in an atom, because all power that's absorbed is re-emitted. So I can re-express this in yet another way as the incident intensity divided by the speed of light times the absorption cross-section times E sub k. Right? Where I used k is equal to omega over c. So this is what we just call radiation pressure. As we discussed classically, if all of whatever electromagnetic field has, if the intensity carries momentum flux, the momentum flux is absorbed, that is the force. But that force here is all of the absorbed power is scattered power. So we often, what we typically call this force is the scattering force. Typically when we'll hear that expression used. It's the scattering force because it's the force due to the scattering of photons. And each photon carries momentum h bar k, and they are scattered at a rate omega s. So the force of radiation pressure is equal to the rate at which photons are scattered times the momentum per photon. And the scattering rate is given here. You remember that this is nothing more than the number in the excited state at steady state times the spontaneous emission rate. Okay? Radiation pressure is then easy to understand. What about this? Well, this is sort of easy to understand too. Remember the saturation parameter is equal to the Rabi frequency squared divided by 2 divided by this Lorentzian, or multiplied by this Lorentzian, right? Often also written as the intensity over the saturation intensity times that ratio. So, my reactive force then can be rewritten as minus h bar delta over 2 omega times the gradient of omega, and then let's see how I want to express this. Right, delta squared plus gamma squared root 4 plus omega squared over 2. All right, that just comes from plugging that expression into that. So this expression can be rewritten in the following way. This is equal to minus the gradient of h bar delta over 2 the log of 1 plus s. Little exercise to try that. How do we interpret this? Well, firstly, what we see, as we've discussed, the reactive force is a conservative force. It's related to the gradient of potential. And that potential is the light shift potential.
So it vanishes on resonance.
It does. Indeed it does. That's because the real part of the polarizability vanishes on resonance. In fact, as we're about to discuss, this force dominates when I'm far off resonance. Now, this is not the most familiar form of this expression. The more familiar form is to look at the case if I have for low saturation. Then log of 1 plus a small quantity is just a small quantity, right? So the light shift potential for S small compared to 1 is equal to h bar over 2 okay, when S is small compared to 1. This expression we recognize. Something we've worked on in homework. This is what we call the light shift is related to what we call the AC Stark shift. They're one and the same thing in this limit. It's this AC Stark shift on the ground state. And we found in homework and in other discussions that this is nothing more than the energy associated with a polarizable particle, which has a polarizability alpha. The real part of that polarizability relates to the the in-phase component of the oscillation, which induces a dipole moment. And that induced dipole moment then interacts with the field, and the energy of that interaction is this. So the light shift interaction can be thought of as the AC Stark shift, in this case on the ground state. And this is the polarizability of the ground state. And that gives me the same energy that I would calculate quantum mechanically. That's what you did for homework, right? So that is also easy to understand. It's just thinking about, the atom is like a little glass sphere. It's polarizable, and that polarizable particle gets trapped in a light field if there is a variation in the intensity as a function of position. If it was constant, if I had a plane wave or a very big Gaussian beam with such a huge width that I don't see any variation in the amplitude, then there is no force. This is also known as the gradient force. So this is sometimes known as the dipole force or the gradient force. Now, what the heck is this log thing about? Well, the point here is that this expression allows for not just atoms that are with high probability in the ground state, it allows for some number of the atoms in the excited state and some number in the ground state. So, recall the AC start shift for a two-level atom. Well, what we found was that if I have a two-level atom, then if this was the excited state and this is the ground state, then one is shifted up, one is shifted down if the detuning is negative, right? And this shift was related to plus or minus the square root of omega squared. One goes up, one goes down. And if the detuning, so this is what we call red detuning. And if we have blue detuning, then the opposite is true. If this is my excited state and this is my ground state in the absence of the interaction, then the effect of the AC start shift is to move it by this amount in the other direction, right? This is the shifted. So, in the context of this force, well, I have some potential probability. I mean, this expression here is just equal to this shift when the Rabi frequency is tiny compared to delta. Okay? That's equal to the light shift. And you see that light shift is negative when the detuning is negative, the red detuning, and that light shift is positive when I have blue detuning. Associated with the ground state. However, if I have some amount in both of these guys, then I need to think about both potentials. And the light shift potential gives rise to a reactive force can be understood as the number in the excited dress state, or the ground dress state, times minus the gradient of the energy of that dress state, plus the number in the excited state, the dressed excited state, times minus the gradient of this potential, or that energy, as a function of position of the atom. So if you plug that in, you get that this is equal to minus the gradient of the light shift potential, where that has that log in it. So, a few more things to say about the light shift potential and the reactive force. The point of the light shift potential is that it in principle can be used as a trap. That's to say, I can create a potential well for atoms based on the optical dipole force. How would I do it? Well, I need to have a variation in the light shift as a function potential that is like potential well. So for example, let me draw it over here. If I have, suppose I have a laser beam. And the laser beam is such that as a function, so the beam is propagating in this direction, and I look at the variation in the intensity as a function of the transverse distance. I will have some kind of Gaussian beam. I want to use that variation in the intensity as a function of position in order to create a trap for the atoms. How should I do it? Well, what I should do is I should detune the light from resonance to the red. Because if I detune to the red, we said that the potential energy is lowered. So if I were to sketch the dress states as a function of this is my dressed excited state. This is my dressed ground state. So if I detune to the red, we say that the atom is a high field seeker. That is to say, its energy is lowered in regions where the intensity is high. At least if it's in the ground state, the opposite is true. If I want to create a trap, though, of course, what I want to do is have the majority of the population in the ground state. Because if I saturate this transition, I mean, up here, it's a repulsive potential. So I want to keep and not only do I want this to be negative, I want it to be far off resonance such that the saturation parameter is small. In fact, if it's in the excited state, of course, you can spontaneously emit. And that's not a good thing either in terms of trapping. So, is there a regime where the trapping is decent? How can we trap without, and can we avoid spontaneous emission? Well, in order to create a good trap, an optical dipole trap, require trapping large and spontaneous emission small. Well, if we want spontaneous emission to be small, we want the saturation to be small, number one. Which we want, therefore, the majority of the population to be in this dressed ground state. And very little in the excited state. The scattering rate in that case, well, then the number in the excited state is just S over 2. And so the scattering rate in that regime, where S is small compared to 1, is S over 2 times gamma. That's an important thing to remember. The light shift, in this case, is H bar S over 2 times delta. So, let's take a look at this. The saturation parameter was equal to so just writing out the saturation parameter. If we want this to be big, and we want the saturation parameter to be small, then we also require the detuning to be big compared to gamma. We also, of course, want this to be big compared to omega if the saturation parameter is to be small. So in the regime, my detuning is large compared to gamma, then what we say is that I'm far off resonance. I mean, we're not that far of resonance to the degree that our two-level atom approximation breaks down. There's lots of energy scales here. You know, the next energy up might be a terahertz away in cesium. If I look at the D1 versus D2 line, 10 terahertz. And D2, you know, maybe gigahertz in resonance. And the line width is 5 megahertz. So there's plenty of room for all of that. And the two-level atom approximation isn't sacred anyway. I don't know what is sacred in life anymore, but that's another story. Okay, so we're going to be far off resonance. So that means I can drop this 1. And what we see in this case is that the scattering rate here scales like the intensity over the detuning squared, whereas the light shift scales like the intensity over 1 power of the detuning. I mean, that's not surprising. This was related to the real part of the polarizability, which goes like 1 over the detuning. This was related to the imaginary part of the polarizability, which goes like 1 over the detuning squared. So if I'm in the wings of the resonance line, the reactive component dominates over the absorptive component, or the dissipative component. Okay? So, in principle, if I have enough intensity around, and I need to have an intense enough laser such that I can compensate a big detuning with a big intensity, then the light shift can be substantial. However, there's this extra power of 1 over the detuning in the scattering rate, which means that the scattering rate will fall off. Which means that in principle, I can keep my atom trapped in this, say, focus of a laser beam for a very long time. Hopefully, pretty long. So that we can do a good experiment. Okay? But, you know, it's all about power. I mean, isn't that life? It's all about it. So if we got enough power, then we can detune very far. In principle, we can make this as big as we can and make this smaller and smaller and smaller. Yeah?
Isn't, when you expose the atom to the laser light, or at least if you're close to the resonance frequency, doesn't it start with the Rabi oscillations then?
No, it's not close enough. I mean, the point here is that the detuning is huge compared to the Rabi frequency. So, if you recall, if we wanted to think about this on the Bloch sphere, we start the atom in the ground state. If I were on resonance, I would get pure Rabi oscillation. But if I start going off resonance, then this is my torque vector. And the bigger this, the closer it is to the ground state, my oscillations look like that. So the probability of getting to the excited state is absolutely tiny when the detuning is big compared to the Rabi frequency. And that is required in order to get the saturation parameter small. Because the saturation parameter is related to the ratio. If this is big compared to that, then the saturation parameter is often written like that. And we're assuming the detuning is huge compared to the Rabi frequency. So we do not Rabi oscillate into the excited state. But instead, the effect of the light is to dress the ground state a little bit, cause a little bit of perturbation, add a little bit of superposition of of excited state character into the ground state, which makes a tiny dipole moment. But that tiny dipole moment interacts with a huge electric field. D dot E then is big enough. Whereas in the scattering rate, the scattering does, this gamma depends on the dipole moment squared. So the dipole that's induced goes like 1 over the detuning, and that's this, but dipole squared goes like 1 over the detuning squared. So that's how we can get away with having a big dipole force and a small scatter. just out of curiosity, how deep is this trap? Like, what in terms of energy or something, temperature? How cold do the atoms have to be if I'm going to trap them here? Well, it depends on this stuff. Let's take a look at it. So the light shift potential is on, if I just think about it, for some, the peak, depending on what the peak intensity is equal to, if I plug in, I lost a factor of 2 here because it was S over 2. Because I remember that expression. Is equal to H bar gamma over 2 times, over 8. I over I sat, I peak, or I sat, times gamma over delta. Okay, so it's an energy. H bar gamma is an energy. This of course has to be something, maybe, 1 over 10, 1 over 100, it depends how many line widths are off, maybe, it's again going to be dependent on the peak. But we need to think about how big this energy is, right? So let's just look at for gamma on the order of a megahertz, then the energy in units of Boltzmann's constant, if I did this calculation right, is about 300 microkelvin. Okay? So, this is Boltzmann's constant. So, what does that tell me? So, if, let's say, whatever, H bar gamma is on the order of 8 megahertz, right? So this, let's call this the light shift, the peak light shift is on the order of 300 microkelvin times the peak intensity divided by the saturation intensity, which for an alkali is about a milliwatt per centimeter squared. Isn't that right? I think that's right. Times how many line widths I'm off resonance. So, if I'm 10 line widths off resonance, then this is 30 microkelvin, depending on how much power I have. I can make this probably, depends how much intensity I get, maybe make it a millikelvin, I don't know, a few millikelvin, if I have a lot of intensity and can compensate. So that means, maybe with enough intensity, is that about right? What do you think about that? Yeah, I think so. I think that's about right. So, one of the morals of this story is you kind of need cold atoms if we're going to trap them. We're not going to use this thing to trap thermal atoms. Well, how the heck are we going to cool? Well, to cool, we need dissipation. And so we return to the scattering force, yes?
Can you just take some atoms that are, let's say, a few 1 or 2 Kelvin, and then a few will be.
You could, absolutely. I mean, if you had a distribution, but where am I going to get my 1 Kelvin atomic vapor? We're not talking about a liquid here,
Yeah.
right? If I want, it's a good point. Like, let's just pour a little bit of liquid helium in there, and just dump it in and bubble, bubble. But the light forces on the liquid are not the same as the light forces on these individual atoms. Now, one can trap little glass balls in a focus of a laser beam. That's what's known as an optical tweezer. And it's used extensively these days in biophysics experiments where you take some DNA or protein or something, and you attach a little glass bead to it, and then you can put that bead, because of course that has a huge polarizability compared to an atom, right? Because the polarizability kind of depends on the cube the volume of the sphere, and the volume of an atom is pretty tiny. So I can trap a glass bead in a focus, and that's an optical tweezer. But if I want to trap atoms for all this fun and profit, then I gotta have them cold. I got to slow them down. So, way to redo that is we think about radiation pressure and the scattering force. And this is the whole idea of lasers cooling. But before we get to cooling, let's analyze a little bit these forces. How big are they? What do they do? We said that the scattering force was equal to h bar k times the scattering rate. And that scattering rate is S over 2. So 1 plus S times gamma over 2. And that's, okay, so let's just think about this for a moment. How big is this force? Well, the maximum that this force can be is when the saturation parameter goes to infinity, which is to say, I've saturated the transition, I have equal populations in the excited state and the ground state, I have half in the excited state, and so the maximum force is equal to that. Or, said another way, the maximum acceleration is equal to the recoil velocity, which is h bar k over the mass of the whole atom times the rate over 2. Okay, so how big is that? Well, if you plug that in, we calculated those recoil velocities last lecture. I don't know what it's like. For sodium, this is like 2 centimeters a second, and with a certain rate of spontaneous emission. For sodium, which was the first atom, neutral atom that this was done on, because of the lasers that happened to be around back in 1980, that this is about 10 to the 6 meters per second squared. So that's pretty big, that's 10 to the 5th G. That's a whole lot of acceleration. one way to understand how strong a force that is, or how much acceleration this scattering force is exerting, is, let's just think about, suppose I have some oven, so making a thermal gas of sodium, and I shine a laser beam which exerts radiation pressure or scattering force that tries to decelerate this beam. So the sodium atoms that are coming out at their vapor pressure are coming out at about 1,000 meters per second. Those are the thermal atoms. Right, that's atoms moving over a football field in a second at thermal velocities. I want to bring it to a crawl. I want to bring it to a stop. How long does my beam chamber need to be in order to, if I could stay on resonance the whole time and saturate the transition and keep it, how long does this thing have to go before I stop the beam? So the work that I do, if I have this much length to stop it, the work I do is equal to the change in the kinetic energy. And if I stop it, that's that much kinetic energy. Okay? So if I then plug that in, and I take this as my initial velocity, what I find is that this is on the order of a meter. If I do that kind of stuff. So that's amazing. I mean, these atoms go from moving over a football field in seconds to just crawling or stopping. Not really stopped, of course, that's at zero temperature, but it gives you a scale. We have to get into the details of this. In fact, this is true for, this is about right for all the alkalis. I mean, the other alkalis have less acceleration because their recoil velocity is less because they're heavier, but because they're heavier, the distance they need to go to get that is also less. So it kind of all compensates. Now, one thing we notice about this is that in order for this to work, we gotta scatter a lot of photons, right? Because each photon ain't doing very much. Each photon is giving it a recoil of energy, which is, a tiny amount of energy. What did we say it was? Like pico electron volts. So in order for us to exert this much force, we need to scatter lots of photons. So it is essential, if you're going to exert these forces, to have what we discussed last time, a so-called cycling transition. It's essential. Because if I scatter one photon and then the atom decays into some other energy level where it's invisible to the photon, well, just scatter one photon because, yeah, sure, give me some stuff. I can take that photon. But if it's like, right? I mean, it's like, you're trying to stop a bowling ball with your ping pong. I mean, each ping pong ball does nothing much, but you have many, many, many ping pong balls, you're going to eventually stop the bowling ball. Okay, now, of course, this discussion at the moment gives us a sense of scales, but if I really wanted to decelerate this beam in this way, I need to be more careful in my description because of the Doppler shift. Because the atoms are moving with a certain velocity. The frequency which they see is not the frequency that is in the lab, but in this case they see it'll see it blue shifted, right? Because they're moving against the beam. So we need to write down this force now more carefully. My saturation parameter now, in this case, has to include the Doppler shift. Remember, delta, so this is delta minus k dot v is equal to omega laser minus k laser dot v minus the resonance frequency. So if the velocity is opposite to k, this is a positive number, which means in order to be, if I'm on resonance, I need to detune to the red. So delta has to be negative if k dot v is negative. So let's imagine I have a thermal beam of atoms. It had some Gaussian distribution of velocities, a Maxwell-Boltzmann along, say, the x direction. Now, of course, for only the ones that are going backwards don't come out. That's okay. Now, let's say that we I detune the laser slightly to the red. I guess I really want to, the way depends how I want to think about it, what's a positive velocity and what's a negative velocity. Well, it's okay. I'll just take k in the negative x direction. Okay? So I'm going to detune the thing such that I'm slightly to the red. In which case I have this Lorentzian that looks like this, where this is where kV is equal to 52. So this is my probability of having a certain velocity, and this is my force, which is a function of velocity. It's a function of velocity because the absorption rate depends on velocity. Okay? So what I see here is the following. There is, around this area, there is the force around this point has a negative slope. This slope, since the force is negative with velocity, means that there is friction. What's going to happen in this case to these atoms? Well, the atoms that are in resonance here start to bunch up. That is to say, the atoms that were moving fast start to slow down. When they start to slow down, they get more into resonance. Eventually, they slow down too much, they get farther out of resonance. So what I'll do in this is I'll kind of, that's not a very good picture. I'm going to take a little clump out of the atoms. the little velocity group, the spread velocities that are on the order of the line width are in resonance with the atoms. So what's going to happen in this problem is that there's a certain small velocity group that see the light. They start to get slowed down. The ones that are a little bit, are in the tails of this, slow down, get even more force, and then they get pushed. Then they're out of resonance. The ones that are right on resonance get a big kick, but then they're out of resonance. And I'm going to get this kind of bunching up of the velocity distribution. At least a little bit. The spread of velocities is related to temperature.
I don't understand why you assume that the resonance frequency is there. It doesn't have to be the Lorentzian curve?
That the Lorentzian curve is the force.
Yeah.
The original was the probability distribution. I have atoms that are not all of the same velocity. They come out with some spread in velocities. The atoms that are moving fast enough, the detuning is to the red. When they start moving towards the atom, when they start moving towards the laser beam, they start seeing the ones that are moving at just the right speed are in resonance. They get a big force.
Is it not the ones that are at the Lorentzian curve at that speed?
Let me see if I have this described correctly. The problem is there are none of these atoms. I'm only looking at the atoms that are coming out of the guys that are moving backwards. I don't see them.
Okay.
So I'm looking at this part of the velocity distribution. And I want it to be that when that if they are moving at just the right speed, coming out of this thing, they see a big force. So I've detuned the low resonance such that when they come to the right speed, because of the Doppler shift, they feel the right force.
But still, in your picture, it is like when they are slowed down, then they get further into the Lorentzian curve, into that area, so they have to be
They're pushed
slowed
even
down more and more.
They're slowed down more and more and more and more.
And
we want them to move towards zero velocity.
Yeah, and then they would all gather at the left of the Lorentzian curve.
Eventually, they would. Yeah, if I had enough force, they would be pushed backwards. Indeed, they would.
So I don't understand why.
But they can't because of the fact that when they do, they get out of resonance.
And isn't the resonance at the peak of the Lorentzian curve?
It is indeed.
So they come closer and closer to resonance.
I think I tend to agree. So they could never bunch there because there's a larger force at zero than there is at slightly positive. So they would get knocked out of zero.
Oh, you're
quickly.
right. I have this backwards. You're absolutely right. That had a positive slope, not a negative slope. I want it to be. You're absolutely right. This is friction. Force. So this group gets pushed. Yeah, I'm sorry, I have that absolutely backwards. The peak of Lorentzium has to be here.
So the atoms with K dot V equal to the detuning see the largest force.
That's correct. That's correct. Yeah. That is correct.
You check the frequency to
Right.
maximum-
So that is indeed the next point, which is that because of this fact that once they start scattering photons, they get out of resonance. If I want to bring a bigger group of atoms to lower velocity, there's a few different ways I can do that. What I need to do is I need to sweep this detuning to move this resonance closer and closer to zero velocity so that I can start with my detuning out here, grab this part of the tail, and move it, sweep it to zero velocity, and in the process, bring all these atoms, make a huge spike, and compress the atoms as much as possible. This is sweeping this detuning. Can be achieved in two different ways. Remember, the detuning is the difference between the laser frequency and the resonance frequency. If I sweep this to zero to zero velocity, I can do it in two different ways. I can change the frequency as a function of time, and that's what's called chirping. The chirp. Or I can change the resonance energy as a function of time or as a function of distance along this beam, and I can do that with a Zeeman shift. So the first experiments, and many experiments that still are done today, if you want to collect a lot of atoms out of an oven, you have a beam and you can use the Zeeman shift. So what you do is you put in here a solenoid with a magnetic field that is changing as a function of distance, such that they're very detuned, and therefore the highest velocity class is in resonance right out of the oven. And then the detuning gets to be less and less and less, so that the slower atoms are more and more and more resonance. And this is what's known as a Zeeman slower. And many of laboratories use this. I mean, Bill swears by it. Any experiment doesn't have a Zeeman slower. He says it's just not the right experiment to do, so I don't know. Okay.
So what's the kind of temperatures you can?
So these atoms are not really, in some sense, at in a kind of thermal equilibrium in this kind, because I'm only cooling in one direction. They're of course heating up in the other direction, and they come out of this Zeeman slower. Well, they have some velocity here. In principle, what we want to do then is to collect them in some kind of area, in some kind of trap, where they come into thermal equilibrium and they have some kind of temperature. And that's what we're going to discuss next week, but let me just give you a little bit of a preview on that.
Just one question. Well, why is the scattering force velocity dependent?
Because of the Doppler shift.
Okay.
So the rate at which an atom scatters depends on how fast it's moving. Because the shift, whether right here, the resonance frequency depends on its speed. What we want to do is to create the kind of force in the accelerating frame in the lab frame. To do that, in the lab frame, we can use counterpropagating beams. So let's just think about this simply for a moment. Let's say I have two laser beams. They're counter-propagating. That are both detuned to the red. Okay? So, here's my atom. If it is moving with velocity in this direction, it gets farther out of resonance with this beam because this one was detuned to the red. Now it's even farther to the red. And thus it feels very little force from this beam. But it's moving, it sees this guy blue shifted, which means that it feels a stronger force from this because it gets closer into resonance with this beam. And vice versa. If it starts moving in this direction, all of a sudden this guy comes into resonance, and this guy gets farther out of resonance. So in this 1D problem, what we see is no matter which direction it moves, it feels a force opposite of its velocity. And this is friction. Such that it's in the lab frame and it tries to slow it right to zero. More precisely, if I look at the force for this guy, what I find is I have what we just described over here. This is the right force. This was our single beam. It's got the other direction. It goes like this. The sum of these forces, so these are my two Lorentzians as a function of the force and a function of velocity. One gives me a positive kick, one gives me a negative kick. The sum of these gives me a force curve that looks like this. With a friction coefficient. And so this configuration is what's known as optical molasses. Because it's like a sticky substance. No matter which direction, at least in this 1D, we don't have to think about it in higher dimensions, the atom moves, it's feeling a force that's opposing its motion. And that is what we call molasses. And it's this that ultimately can cool the atoms, slow them down, and get to temperatures that are related to this effect, which is known as Doppler cooling. And that Doppler cooling temperatures are on the order of millikelvin. So it's a very simple mechanism. We need to figure out what sets this limit of temperature, because right now it just looks like it's just slowed down. Why does it speed up? The reason, of course, is that in addition to the effect of the friction, we also have the effect of the recoil. The recoil can give rise to heating. And it's the balance between the heating and the cooling that will set this ultimate temperature. So we'll discuss that next time and we'll put some notes on for you guys to look at. All right?